today is lecture 7. We are going to cover a actually very interesting but very theoretical topic called linear regression models with regularization. So just to, again, using our nutshell views to look at this new set of methods we're going to cover. So again, everything is very similar, almost the same as linear regression. And the changes is, we're going to change our loss functions by add some kind of regularization laws. The regularization are normally the norm functions on your weight factors. And because of these changes, so the if you do the L2 type of, it really results in the revised normal equation solution and also a revised actually non-gradient descent. There are many variations try to solve some called subgradient descent or proximal based method. So we're not going to cover here. So you can think about their slightly revised version of gradient descent as stochastic gradient descent. And why do we want to add regularization? And the main purpose, in fact, is to make the model more robust and more interpretable and also more scalable. All right, so let's come here. So this is, again, like I just mentioned, we aim to make our trained models not just generalize well. It's not just to predict the future data. And we also want our model to be interpretable, to be relatively robust. So, but in fact, in the real world data, there are many real world data sets. They're not as clean as those really nice, correct labels and also p larger than n and many n. So there are many tasks in the real world. Very classic issue is, especially in biomedicine, is the p is actually much larger than n. So for example, so this is a really classic task, using gene expression based patient representation. So we can think about each row here is a patient blood sample, and each column here different kind of genes, and you measure how the quantities of that gene in these blood samples. So this is the first gene, second gene, and then so on and so forth. There are actually a lot. And then you, in your patient, this blood sample, so each one of them, the row is a blood sample. And then they can be two groups. So in this case, if I remember correctly, one of is the control group, which means there's no cancer, and the other group is this leukemia group. It's a cancer. They are the cancer patient. So actually, in fact, this is the patient group. That patient group. I remember roughly the control group in this data, it's about 40. And the patient group, the number of patients, it's about 30. But the number of the genes you can measure the expression is actually much larger. And so we actually know that human, the gene space is 30,000. So this specific work measured about 2,000 genes expression values. So we can actually see this X. So this is our current X, and it has P, it's about 2,000, and N, it's about 70, less than 100. P is much larger than N. And this is not a very uncommon case, and I think the majority of the biomedical, a lot of biomedical data, the cases is, we have the ability to measure thousands or maybe millions of genetic informations. We don't have that amount of patient information. Of course, people are trying really hard. I mean, if you ever know like UK Biobank, and there are many like different organized scientific studies trying to improve and make the N larger. But so far, most problems are still in this regime of P larger than N. All right, so this data is actually one of the Kaggle competition. You can just click the link, go to Kaggle, and there are quite a few like different kind of notebooks just show you how to handle this data. And first, I mean, you have to clean the data because there are just so many genes. There's a lot of noise and maybe like housekeeping genes, although you have to remove those. And so, I actually told you wrongly. This is not 1,000. This is actually 7,000 genes. So the P, it's actually around 7,129. Yeah. All right. So let me revise my. This is like 7,000 versus 70. Yeah. So even more dramatic than I previously realized. All right, so this is like 7,000 features, about 70 data. And how can you handle this? Just think about, I mean, it's extremely difficult to figure out. Can I use a future blood sample gene expression vector to predict what's the risk of this potential patient's leukemia risk? So let's come back. So this, not even to mention, we just told you like N equals to about 70 in the previous task, right? And we also need to actually perform model selection. If you still remember the last section we covered, so it's not just to train and test. It's not just two modes, and we also need to have some other validation mode. If we adding that into this use of our data, there's only like about 70 samples, and then I have to split into training purpose and validation purpose for model selection. This is model training, this is model selection. Testing is to it's just to like observe, I mean, this future performance. And this makes it extremely difficult with the P about 7,000. All right, so one solution can be just we make that P smaller. So rather than using all the P, can we have select just subsets of the features, and hopefully the subset is much smaller than the N, and then we can use everything we had. I mean, I will tell you why make N larger than P is good. I mean, after actually the first module, like theoretically, P larger than N is actually bad for regression. And we're going to prove that later. So just keep that in mind. So one way is we try to reduce the P into smaller P prime. But how, right? I mean, there are actually a huge group of methods called feature selection, which we will not cover here. And which we're going to cover today is the approach called regularization. You can think about regularization is doing some implicit. It's an implicit feature selection. So regularization. All right, so that's set up the scope of really what is regularization is doing. It's some kind of feature selection. And so why do we do feature selection? I mean, first of all, it's much easier to understand. I mean, it's also much more robust and doing this. So this is the top method people use, I mean, on this type of data. I mean, it's PCA. I mean, we're going to cover that later. So what we cover today, I mean, it's not like a PCA type. So let me maybe again. So we are doing implicit feature selection based on regularization in the original space. The very popular approach, I mean, people from biomedicine maybe know about this really, really well. This PCA approach, in fact, project from the RP space into a lower dimensional space. We just call that RP prime. But this RP prime, it's not a subset of the original space. It's a constructed lower dimensional space. So there are some differences versus the PCA. So this is a new space. And the implicit feature selection based on regularized version like lasso, the P prime actually, it's part of the P. Yeah, so this is that. I mean, you can think about I'm selecting features. How do you select features? The easiest is I'm learning a weight vector by pushing most of the weight, those weight as 0. Theta x around 0, theta p. Theta sum features, yeah. So this subset as 0, and that's the implicit feature selection. All right, so let's use another example. I mean, not just biomedicine based. I mean, so regression seems to be less used in this like internet-based application. But I think this paper gave you a pretty good example. Regression can be still very helpful. So for example, this paper is from HRT. I mean, they're using this movie reviews and metadata of movies and to predict the first open days revenues. And revenue, because that's a number and numerical, so this formulation itself is a regression task. And you actually can just directly download their data. And this data, I tried to make a Jupyter notebooks, but the data is kind of relatively large, like 40 megabytes of data. So I gave up before like our class. So let's just see. Long story short, the data is, I mean, the features are metadata and critics reviews, and the feature it's not like automatically learned. I mean, features are mostly hand engineered. There are metadata like genre, readings, running time, actors, directors, and from this website, metacritic.com. And there's also the reviews from different resources, and then and their Y. So this part is their X, and this part is O. So this part is the Y. Yeah. So Y is a number. Is that open weekend revenue? So it's a numerical number. So it's a regression task. So this is actually the number, the sample size. The whole sample size is 1718. N. So this is their N size. They split it, in fact, into train. Like this is validation, they call that develop set, and also test set. So again, emphasize training is to optimize the loss function to get our model, and development is to do model selection and hyperparameter tuning. Test is to give you to assess how your model work assessment. Model evaluation. Yeah. All right. So, so this is the features. They used like n-gram feature, part of speech feature, dependency relay. There are actually a lot of hand engineering here, and I remember this has about more than 3K features. So again, so N is about 1,700, and then P is like 30,000. So this is roughly like 20 times. Yeah. Yes, it's 20 times. Okay, so again, so this is large P, a small n, and this paper, in fact, use approach. It's exactly what we're going to cover today. it's a regularized regression. And the first purpose they do this, I mean, it's about easy to understand. And the other, it's also robustness, we're going to cover in the second module. Okay, so this is the model they used. So this model is called elastic net approach. And don't worry about the terminology, and then it's actually very, very simple. And so this part is the loss function, y minus yi predicted, cover all the training data. So this is just all your training data. So this is the loss part, or the cost function we call it. And you just augment this loss function plus this called p beta. We normally call this penalty function because it's trying to penalize the size of the beta vector, the beta weight, and we are going to talk about what do we mean penalize. So in fact, it's the whole effect is shrink. It shrink the beta to be not too large. And specifically, and this beta p beta function is a summation of L2 norm and L1 norm of the beta vector. So I hope you're doing the homework one, and in the homework one, we ask you what is a vector's L2 norm, what is a vector's L1 norm. So L2 norm of a vector is just, actually this is L2 square. It's really just summation of all the elements, take a square. And then here, if it's norm, there's a square root, but we are using the quadratic form, so which is just a summation of the two quadratic form. And L1 is just summation of absolute values. And I hope you already done this homework, so it should be very apparent. So this is a weighted sum of L1 norm and L2 norm of the weight vector we need to look for, okay? Beta is, so in here, just writing as beta is the one we look for. So in fact, I mean, they only penalize on those beta, we used to call that theta, on these x, they're those called weights. This portion is called weights, and this pseudo term is normally called bias. So, so this is the weight part, and that specific weight you're looking for to the intercept term is normally called bias term. Yeah, and the penalty is normally most only applied on the weight vector part, not on the biased part. And there's a lot of reason to that. I'm not going to talk about why. All right. Okay. So let's generalize this into this more like explicit form. I mean, the previous formulation is just for that specific application using elastic net, and we're going to cover actually a much simpler version than those. So we can actually tell, and we can append our loss function, the error on the function, the cost on the function, plus some kind of norm on your weight vector. If you add the L1 norm weighted by a lambda parameter, so this is actually called shrinkage parameter, or we just call that hyperparameter. And this whole thing is called lasso estimator. If you only include the L2 norm part, and this is called ridge regression estimator. Ridge regression, if there's only lasso, only L1 is called lasso. If there's only L2 norm of your weight vector penalty, it's called ridge regression. And if there's a weighted sum, you already know from the previous page, this is called elastic net regression, which we will not cover. We will cover the individual and how to solve them in this lesson. All right, so you can actually tell, And the regularized linear regression is a revision on top of the classic linear regression. It just adds this norm function, norm on the weight vector, do a summation. You try to minimize not just the error on the data, you also try to minimize the norm of your weight vectors. So this is really what it does. Okay, so let's see the influence, see the results from using this elastic net regression model on that data. So this is in fact the weight vector you learned. And you actually can sort it, right? Because there are different numbers. You can just sort them. And the very red ones are really, I think this is a minus. This is the minus influence, negative influence. And the green one is the positive influenced. And each one of the weight vector corresponding to a feature. And feature weights can be interpreted and then directly by the US dollars, because this is a regression test, right? You can see the ratio, how much my feature contributes to that final Y. Okay, so let's see what contributes positively. So in fact, because there are 7,000 features, right? About, oh no, actually 3K features. So the majority, in fact, are close to 0. The majority of the weight are pushed as 0. And on the positive side, you can see midlife crisis, anticipation, and wills. And this is actually in 2010, right? If you have this type of keywords and the revenue is a positive influence on that revenue on the first day. And if you have, let's look at the negative side. Okay, so if it's documentary, it's actually a negative impact. If it's philosophical, it's also a negative impact on the revenue. So, this is pretty straightforward and help you to explain truly what influenced the revenue and this kind of interpretable model. It's not just to predict future prediction, right? And hopefully there's some kind of movie designer or publisher can get insights from here and then try to do some better branding of their movies, hopefully to earn more. So this is really the purpose. Why do you need an interpretable model? All right, so this tells us shrink a majority of the weight and leave just those really important weight vectors. It's good, and we like that. So, okay, so let's summarize. So we have, we just append this regularized penalty norm function on the weight vector on top of our loss function, and we try to minimize that. And this gives us a regularized linear regression models. And this type of models, the first apparent good property is it gives us more interpretable models. And in the next module we're going to talk about, it also gives us robust, predict better models just based on that formulation itself, especially in those bad cases. So to summarize, actually, we can generalize this L1, L2 norm to even more generalized form. This is called Q norm. And I hope you learned it in your maybe linear algebra class. So 1Q equals to 2, we got our ridge regression. 1Q equals to 1, we get our lasso regression. And you can also have other numbers, in fact. And I included the property of this type of norm function in our extra slides. So there are a lot, and also geometric interpretations in our extra slides. But I will not cover here because I feel those are too theoretical. So I only cover in the graduate level class on those. Okay, so this is the end of this first module. It's a basic introduction of why do we need regularized models, and